I'm Nico. Let's talk about PDE solvers. So traditionally, when you solve a time-dependent partial differential equation with a technique called the method of lines, what you do is you introduce a spatial grid, and then on this spatial grid, you approximate the differential operator with a matrix vector product, for example, with finite difference schemes. This turns the partial differential equation into a system of ordinary differential equations, which can be solved with any ODE solver, including probabilistic solvers. However, there's one big issue with this approach. The approximation error made by the finite difference approximation completely messes up the uncertainty calibration of the ODE solver. Why? Because, simply put, the ODE solver does not know whether it is solving any ODE or a discretized PDE. For example, if we look at the chi-square statistic, which is a measure of the uncertainty calibration of the ODE solver, then we see that with traditional solvers on the right, there's a very clear correspondence between for which delta t and delta x steps the calibration is actually good, indicated by yellow. For other configurations, indicated by blue and red, the solver is either extremely over or underconfident. But this need not be the case. For example, on the left here, with a fully probabilistic method of line solver, we see that the calibration can be good for all delta t, delta x combinations. So how does this work? There's two ingredients for the probabilistic numerical method of lines. The first one is a probabilistic take on finite difference schemes, which is essentially a translation of finite difference schemes to the world of Gaussian processes. The second ingredient is a probabilistic ODE solver, which, as we found out recently, is very good at inferring latent forces in the ODE itself. These two components together make up the probabilistic numerical method of lines. So in summary, now we can use probabilistic ODE solvers to solve time-dependent PDEs. This has been joint work with Schmidt and Philipp Hennig. Have a look at our paper and drop by the poster on Monday. Thanks.